Uh, okay, so good evening. Okay, so we'll start this live session. So today we'll solve some basic problems from the topic that you have learned in the week 6 lecture video. Okay, so these are basically the frequency response. So they this board plot and the polar plot of the Nyquist plot, and you have also learned phase margin, gain margin. We'll solve some basic problem related to these topics. Okay, so we'll start some simple questions. So we have a second order system. Okay, so the transfer function is given, and you are given that the percentage overshoot, that is the time response, this MP, it is 10%, that is the 0.1. So then what should be the resonant peak, that is in the board plot. Okay, so I'll start. Paul, you can answer, then we will discuss. Okay, so okay, so you know that this resonant peak, this formula is dependent on your damping factor zeta. So you have to first find zeta using the given data, that is the percentage overshoot. Then you can find like this peak, resonant peak value. Okay, so we can discuss this now. Uh, you know this, like if the percentage overshoot is given, then how to find this damping factor. Okay, so because you need okay, first you write this formula for this resonant peak, which is very simple. Square root of 1 minus zeta square. Okay, and this is valid only when zeta is between this. Okay, you already know this. So for zeta value higher than this, there is no peak, resonant peak. Okay, so for this it is valid. So if you know this zeta value, that is the damping factor, then you can easily calculate by just substituting that damping factor value, zeta value. Okay, so and you are given this percentage overshoot, so you are given this MP 10%, which means also 0.1, and you know this damping factor is simply I square plus ln square MP. So this is from from time domain response. So you just substitute there, instead of MP you just substitute 0.1, so zeta will come out. So ln 0.1 pi square plus ln 0.1 square. So this is for MP equal to, substitute MP equal to 0.1, so it will come out 0.59. Okay, so you just substitute this value in this resonant peak value, then you will get this answer. So MR will be 2 times of 0.59 1 minus 0.59 square. So it is okay, so 2 times of 0.59 into 1 minus 0.59 square, so it's around 1.05. Okay, so this is the correct answer. Okay, so again this question is very simple. So you just because you are given percentage overshoot, from that you find that damping factor, that is the zeta value, what should be the value for this. So this is this formula, you remember this from time domain, the time response.
Hello.
Yes.
Sir, can you increase your volume?
Oh, okay, yeah. Can you hear me now? Okay.
Sir, your voice is clear but a little low. So can you please increase your volume?
Oh, okay, okay. Okay, so am I audible now? Or still you have this problem? Okay. Okay, am I audible? Hello.
Yes, sir. Now you are audible.
Okay, okay. So sorry for some that issue. Okay. So as I was saying that because this you are given percentage overshoot, that is the MP. So from this you already know how to calculate this damping factor zeta. So then you just substitute in this formula of resonant peak and you will get this. Okay, so this is just very direct question. Okay, so we can then move to the next question. Okay, so you are given GS value, that is upper loop transfer function, and you are given the Bode plot of this. Okay, so the Bode plot as you can see here it is given. So then you are asked what is the value of the K. So from this transfer function, as you can see, there are some unknown quantities like K value, A value and B value. These are not given there. So you have to find what is this K value such that this is the Bode plot that is actually shown in there in the figure. Okay, so you can answer through a poll, then we'll discuss this. Okay. Yeah. Okay. So one hint will be like to find this K value, you just look for low frequency range, right? So because you have a pole at 0, I mean at the origin you have a pole from this, so the initial slope will be minus 20 dB per decade, and from that data you can find this K value from this initial portion of this Bode plot. Okay, so try this. Okay, so we can discuss this. So as I said, from the initial portion of the Bode plot we can find this K value when S is very small. Okay, that is the initial portion of the Bode plot, it is this frequency, because S in the Bode plot you use S as the j omega, right, this frequency. So when this frequency omega is very small, okay, very small, it's positive still but very small, then some number 1 or epsilon I can say, just represent it to be very small. Okay, it's near about 0, when omega is very close to 0 but still is positive. Okay, so that person, from this transfer function, as you can see, all the terms 1 plus 0.5 into s, 1 plus as, everything you can ignore, because this term will be like 1 plus, for example, some factor as is there, because this is very close to 0, so it's approximately equal to 1, right? So your gs can be then written or j omega, I will say, because we are dealing with frequency response. So j omega, it can be written very approximately, because all other term will be 1, only this gain will be there, and this pole that is present in the origin. So this will be the approximate value of g, as the omega is very small. So from Bode plot, you know that a pole at the origin will give a slope of minus 20 dB per decade, and this is exactly what you see in this Bode plot, right? And you see that when this magnitude will be, that means this Bode plot is plotted like this, because it's dB, so you have this magnitude of j omega. So the initial person, it will be 20 log k, and this magnitude is simply omega, right? And you see, when this slope line, actually this is the 0 dB line, so when it actually hits this 0 dB line, and 0 dB means your magnitude should be, logarithm of 1 is 0, so its magnitude should be 1, so this equal to 0 you can put. Okay, at some frequency this 8, right? So let's denote it omega 1, so at omega 1 it is 0, right? From this you observe this, so or k by omega 1, it should be equal to 1, because the logarithm of 1 is 0, right? So simply you find k equal to omega 1. So this is basically the initial line, that is this initial 20 dB slope that actually hits this, or its extension, because it's ending there, its extension where it meets the 0 dB line, or magnitude of 1, this gain. Okay, so 0 dB, it is also equal to 1, magnitude of 1. So then from this relation you find that it's exactly this frequency at which it hits, numerically equal to the gain value of k. So this is 8, so correct answer is 8. Okay, so the next question, again the same data, and you have to find the value of a and b. Okay, so okay, I will just, okay, so a is the 0, and b actually, I mean it's not 0, 1 by a is actually the 0 position, and 1 by b is actually the pole position. So you have to find this using that Bode plot, so you can answer through pole. Okay, so we can discuss this. So again, very simple question. So you just point out like this corner frequency, because all these factors are first order factors, so you have to find this corner frequency where this change of slope actually happens. So for each pole you have a minus 20 dB slope, and for 0 because it is in the numerator, so you have positive term, that is the 20 dB per decade. So using that you can find like what the other value of this A and B are that are not accounted in the figure. Okay, so let's see just so you have one corner frequency is 8 where this pole will be located, and another is 1 by B, and this is 36, and from this you have so it is 2 yeah, so 1 by 0.5 is 2, right? So 2 and 1 is A. So these are the 0 and these are the pole, and initially also you have a pole at the origin, this is. So initially you have 0, means it's from beginning you have a minus 20 dB per decade slope. Then you see at the 2 this 0 occurs, so you have minus 20 plus 20, so 0 dB slope is there. Then you have another at the point 4, so you have not accounted that 4, so 1 by B should be equal to 4 or B equal to 1 by 4, right? So at that pole again your slope it should be A, right? Because this is 20 dB per decade, so positive, so it should be A, not pole, right? So it should be a 0, so your A should be 1 by 4, and then you at the 8 you have another pole, so 20 dB plus minus 20 dB, so this is 0 dB, and at 24 you see another pole should be there because you have minus 20 dB per decade slope, so 1 by B should be equal to 24 or B equal to 1 by 24, and then finally at 36 you have another pole, so the slope actually changes to minus 40 dB. So you see you have already accounted for all pole and 0, so from that you just calculate A and B. So these are 1 by 4 0.25 and B 1 by 24, it is approximately equal to 0.042. okay, so then we move to the next question. Okay, so you have a transfer function which have only 1, 0 and 5 poles. So the slope of the Bode plot, when this frequency is very high. Okay, so you can answer through poll, then we discuss. Okay, so one thing to notice here that it is not mentioned whether this system is a minimum phase or non-minimum phase system. Okay, so this is because for both system the magnitude plot will not be different, only this phase plot will be different. So it does not matter where your system is minimum phase or non-minimum phase system. Okay, if you are just considering this magnitude plot. Okay, okay, so again very basic question. So you have 1, 0 and 5 poles, and you already know that your 0 will contribute 20 dB per decade, so the positive 20 dB per decade slope, and your each pole will contribute minus 20 dB per decade. Okay, so irrespective of where they are located, whether poles are at the initial position or the 0 is at the initial position or they are intermediate between it, when this frequency become very high, so you have already passed through all this corner frequency, right? Like this, you already passed through corner frequency, so your final slope will be determined by how many poles and 0 are there. So for each 0 you accounted for like 20 dB per decade, and for each pole you have minus 20 dB per decade. So finally, so it will be 20 dB per decade for each 0, and for each pole you have minus 20 dB per decade. So when you pass all these zeros and poles, then for each zero you have this contribution, and for each pole, so there are 5 poles, so this contribution will be there. So in total you have 4 into minus 20 dB per decade, right? So this is the contribution that will happen in the final slope. That means when this frequency is very high, so it is minus 80 dB per decade. Okay, so this can also be seen from the difference, that is the pole minus 0, so it is 4. So you have, this 4 should be, 1 0 and pole, this is minus 20 and 20 will be cancel out, so only other 4 poles contribution will be there when this omega is very high. So and for each pole you have minus 20 dB per decade, so for 4 pole it will be minus 80 dB per decade. Okay, next we move to question 5. So here you have some system is given, so you have to find the transfer function. So I am not given any option, so I will just derive this, and from this you just plot this Bode plot of this system. Okay, how this frequency response of the system will be. Okay, so you see one dependent source is there, and this is the output and this is the input. So to find this relation between input and output, you have to find this V2, and then depending on this V2 value, so this is a dependent source here, so then you can find this V0 in relation to V1. Okay, so we will just compute this. So just voltage division rule. So first in the frequency response, this will be R1 and this will be 1 by C1s, and this term will be 1 by C2s, this impedance in the Laplace domain. Okay, so this will be R2 only, so you know this. Okay, so then you have V2 will be equal to just voltage division rule, so you will just find this voltage around this point. So this will be just this multiplied this voltage across this by summation of these two impedance. Okay, so this is just 1 by C1s by R1 plus 1 by C1s time V1. Okay, so this is just 1 by 1 plus R1 C1s V1. Okay, so again you apply this voltage division rule here. So your voltage at V out, V0 will be just R2 by R2 plus 1 by C2s time KV2. R2 by 1 plus R2 C2s KV2, and KV2, I mean you have already computed a V2, so you just substitute there. R2 by 1 plus R2 C2s into 1 plus R1 C1s okay, so we have C2 also there, right? S C2s, right? K times V1. Okay, okay, let's compute this. So this is the transfer function, so V0 by V input, so this is the transfer function, and so this is K R2 C2s by C1s times R2 C2s. Okay, so the next question, you just try to plot this transfer function. Okay, the Bode plot of this transfer function when this condition is given. Okay, okay, so to plot this, so you see that these are the two corner frequency, right? 1 by this R1 C1 and 1 by R2 C2 will be the corner frequency, because we want to plot this, and two poles are there and 1 0 is at the origin. Okay, so the initial slope will be what then? And because 20 dB, and
देख लेना
Okay, so and it is given that R2 C2 is greater than R1 C1, so it means that 1 by R2 C2 will be less than 1 by R1 C1. So the initial pole, I mean this corner frequency, first corner frequency will be what? 1 by R2 C2, and the later corner frequency will be C1. Okay, and the initial slope, because of this 0, it will be 20 dB per decade. So you have a, okay, and what should be this value? Can anyone say?
VO.
Yeah, no, I mean from this transfer function, you just ignore this because this is immaterial to us now. We are just considering this transfer function. Okay, yeah, so somebody has answered 20 log k. So it's just this asymptotes, right? So it's just increasing in the value of 20 dB per decade, and so around this point it will have gone to 20 log k. So this is approximate plot, so the value will be different at this point. Okay, then you have a pole there at R2 C2 1 by this pole. Okay, so you have minus 20 dB plus 20 dB minus 20 dB, so 0 dB slope. Then again you encounter another corner frequency at 1 by R1 C1, and this is a pole there, so you have minus 20 dB per decade slope. Okay, so this will be the Bode plot. Okay, so this is asymptotic, as you already know, because okay, so one thing, when this frequency S is this one, because at this point this is the S value, right? S or omega value. So if you substitute that value, you see that this is not exactly 20 log k, right? It will be different because these are asymptotic plot, right? It will be something like this original, I mean this exact plot, but you are just plotting asymptotic plot. So that's why this is just asymptote, and this value will be 20 log k. Okay, is it clear? Okay, so this is just asymptotic plot. Okay, Bode plot is asymptotic plot. That means when at this corner frequency, it will not be the exact one, right? For the first order system, you have already learned that Bode plot, it will be some error will be there at the corner frequency, but as you go very low, I mean very far from this corner frequency, the plot will be exactly, it will match these asymptotes, like, because this you are just drawing straight line, these are asymptotes, and at this corner frequency there will be some error, but as you move away from this corner frequency, both, it will just be like a given by these asymptotes. Okay, so this is just approximate value of this 20 log k as it is given by this asymptotes. Okay, so then we move to next question. Okay, so you have a unity feedback system, a pen loop transfer function is given. Okay, so then what value of k, okay, so which will actually guarantee the gain margin of the system will be 6 dB. Okay, so you can answer through poll. So any doubt in the question, or the question is clear? So you can also ask if something is not clear regarding that question. So you are given some open loop transfer function, and this, yeah, okay, you don't know, okay, just try. Okay, so you know these basic things, right? When this what is called this gain margin and phase margin, so you just apply this basic definition and try. Okay, anyway we are going to discuss, so you just try. So this is you can remember from this. So your instability point will be what? When your gain is 1 and your phase is minus 180 degree, right? So how far you are from this instability point? So if you are in the stability region, and so you can increase your this gain, and see how much you can increase your gain till you actually reach this instability point. So this actually gain is actually it gives your gain margin. Similarly for this phase also, so if your magnitude your gain is like 1 there, it should not be minus 180 degree there, right? Otherwise it will be unstable, the system will be unstable. So if your angle is actually less than minus 180 degree, so then how much phase actually you can actually allow for shift till you reach that instability point. So this actually gives the, yeah, okay, so you can answer through poll. Okay, so there you can see the poll, right? You can answer. Okay, so let other try, then we will discuss. So just apply this basic definition, then you can find this. Okay, just try. Okay, so we'll discuss this anyway. So you are given this open loop transfer function, and you require a gain margin to be 6 dB. Okay, so for gain margin, so where you actually compute this gain margin? So okay, your system will be unstable if this phase angle is minus 180 degree, and at the same point your gain is actually 1, right? Or in the dB it should be 0. If this is happening at the same frequency, then you are in the verge of instability, right? So if your your phase angle is minus 180 degree and your gain is actually less than 1, then you can increase your k value up to certain point. When this k actually become 1, then you are entering that instability region. Okay, so this much of k, how much you can increase, will give you this gain margin, right? Is that clear? So let it be phase crossover frequency. So at that point, so this phase crossover frequency is defined when this angle of this j omega, it's actually minus 180 degree, right? So omega ps. Okay, so if you put this value, you just substitute this omega value, for which value its phase angle is actually minus 180 degree. It's called the phase crossover frequency, because it's just crossing that 180 degree phase line there. Okay, at that point, what is this gain of the system? If this gain of the system is less than 1, that means your system is stable, right? Because you are not encircling that point, you are not encircling that minus 1 plus j0 point. Okay, So that actually gives this instability, right? So if you are just right of this, you are not encircling that point, then your system is stable. So when you reach this point, so this is plot, so this is the, let this point be -1. So as you increase this gain, so this transfer function will just, sorry, this polar plot will encircle this -1 point, right? So how much gain you can increase till it actually reaches this point. Okay, so let's draw this point here. Okay, so let this be some plot. Okay, yeah, so you just compute this phase crossover frequency. Okay, just I am just explaining it more detail. So this is -1. So at this point, it is this phase crossover frequency, because this is the angle, right? -180 angle. From this also you can compute. So you just compute what is this gain of the system and how much you can increase this gain. This gain will be increased by this k value, right? How much k you can increase till this plot actually comes like this. It reaches this instability point. Okay, so this frequency at which it is crossing is called this phase crossover frequency, right? So we first compute this phase crossover frequency. So for that, you find this angle. So this phase angle will be given. So this pole, it will contribute -90 and this will be -10 of omega by 6, right? So this is your angle, and at the phase crossover frequency, so let omega pc be the phase crossover frequency. Okay, then at that point your angle will be -180, right? So this -90 -10 inverse of omega phase crossover to 6, it will be -180. So you just solve for this omega pc, that is the phase crossover frequency for that. So it will be you just solve, that will be 10 inverse omega phase crossover 6, it will be 180 -90, so it's 90. Okay, sorry, there two poles are there, so two times, right? Okay, because the multiplicity of pole at 6 -6 is 2, so we have 2 times, right? This, so each will contribute one angle, so -10 inverse omega by 6 -10 omega by 6, right? So 2 are there, so 2 times is there. Okay, or 10 inverse omega pc by 6 will be 45, implies by 6 will be 1045, and this is equal to 1, right? That means your phase crossover frequency is 6 radian per second. Okay, so once you get this phase crossover frequency, you just compute this gain of the system, right there. What should be the gain of the system, and you want that gain of the system. Okay, you want this phase margin, gain margin to be 6 dB. So that means your gain should be what? If it is at the instability point, it should be, gain should be 0, right? And if it is actually to the right of this, your gain should be less than 1, or in the dB it should be negative value, right? So you take, so your gain at this point, phase crossover frequency, what is this gain? You just put this magnitude of this, so it is the 20 log k by omega pc plus 6 square. Okay, or j omega you can put, then you just take the magnitude. Okay, this should be, what you need this, it should be -6 dB, right? Because you want a gain margin of 6 dB, that means it should be below 6 dB, below that 0 line, that is -6 dB. And you just solve this, so it will be log k by, so this magnitude I write, so it will be omega pc into square root of this, because 2 poles are, so square root of square, so it will be just omega pc square plus 6 square. Okay, this magnitude, this equal to -0.3, or implies that k by omega pc, you can just substitute that value 6 we computed, so times 6 square plus 6 square equal to 10 to the power minus 0.3, or k equal to, just solve that. Okay, I'll just use calculator. Plus 3.3 so it's 216.5 approximately. Okay, so this is the value of k for which your system will have a gain margin of 6 dB, right? Is it clear? Okay, so we are just using that basic definition, nothing else, right? So because you need a gain margin, so this gain margin is defined as the amount of gain you can increase at the phase crossover frequency. That means when this your plot is actually passing through minus 180 degree phase, how much gain you can increase. Okay, so for that you first find this phase crossover frequency where it is actually crossing that minus 180 degree, and you need this gain to be, how much gain margin is given. It should be below that one line, so it is given 6 dB, so it should be minus 6 dB gain should be there, right? So then you just compute that k value that will make this gain to be minus 6 dB. So that means your gain you can increase till 6 dB till it reaches this instability point, right? That is the minus 1. That is, it should be gain 1 and the phase angle of minus 180 degree. Okay, so then we move to the next question. So again, this is similar type of question. So you are given an open loop transfer function, and now you require value of k that should actually give you a phase margin of 40 degree. Okay, so again you just use this basic definition of this phase crossover frequency, gain crossover frequency, and this phase and gain margin. From that you can simply compute this. Okay, so you try and answer through poll, then we will discuss. Okay, again you just use this definition. From that you can easily compute this. So you define this phase margin at what frequency? Can anyone say? Yeah. So your gain should be 1. Yeah, gain should be 1, and you need your phase angle there to be something, so that it will give you some margin error, right? So up to that margin of error, you will be in the stability region. If you increase get over that margin of error, then you will reach that instability region. So this is that from definition. So you just apply that and you can solve. Okay. Yeah, so then we will discuss this again. So again, this question is similar to the previous year question. So only instead of gain margin, you just need this phase margin. So the approach will be almost similar. So this phase margin, as already you have said, it will be defined at the gain crossover frequency. That means when this gain is 1, or in the decibel it is 0 dB, then what is this phase angle of this system, and if it is less than minus 180 degrees, so how much angle lag you can still give till it reaches this instability region, that is the minus 180 degree, right? So phase margin of 40 degree means what should be the phase of that system at this gain crossover frequency? So can anyone answer? So what should be this phase angle at the gain crossover frequency? That is when this magnitude is 1. What is this phase angle of the system? Okay, so your instability
minus 180 degree plus theta.
This 40 degree it is given, right? So at the instability
Minus 180 degree plus
40 degree, so it's minus 140 degree, right? Yeah, so because this phase margin is
Yes, sir.
given as 40 degree, so which means how much still phase lag you can afford to get to the point of instability, that is the minus 180 degree at the point of gain crossover, that is when this system gain is 1. Okay, so let the gain crossover frequency be denoted by this. So at this point the phase angle should be minus 140 degree as you have told. So then you can still afford up to minus 40 degree phase lag, right? So till it reaches that minus 180 degree, so that will actually give this 40 degree of phase margin. So you are given at this gain crossover frequency, this is the angle minus 140 degree, that is the angle of the system. So from that you can easily compute this gain crossover frequency. So what is this angle? J omega, yes, J omega. So k is just constant term, so it's contribute to 0 angle. So this pole will contribute in positive way, so it is omega y. So 4 and 2 poles are there, so this 0 will contribute in positive way and the pole will contribute negative way because it's in the denominator, and each pole will contribute because it's j omega, right? This imaginary part, and so real part is 0. So tan inverse of infinity, it's 90 degrees, so each pole will contribute 90 degree, and there are 2 poles, so it will contribute 2 into this, right? So this should be equal to minus 140 degree, or sorry, at the gain crossover frequency. So this is just angle, and when you put this gain crossover frequency, that is j omega gain crossover frequency, j gain crossover frequency, so this angle should be minus 140 degree. So this is tan inverse of omega gain crossover frequency by 4 minus 180 degree should be minus 140 degree, or implies that tan inverse gain crossover frequency by 4, this should be equal to this is just 40 degree, right? Or 4 will be 10 40 degree, 10 40 degree, or omega gain crossover frequency will be 4 times into 10 40 degree. So you just compute this, so using calculator I'm just computing, so it's 4 into 10 or 40 degree, so it's around 3.36 radian per second. Okay, so once you find this gain crossover frequency, then you find the value of the k for such that this gain will be 1, right? So that means, or this in that dB it should be 0 dB. So this gain means this k by j gain crossover frequency plus 4 by j gain crossover frequency square. This magnitude should be equal to 1, or when you put 20 log dB it should be 0, right? So either of 1 you can use, okay, because the logarithm of 1 is 0, okay. So implies that k and this magnitude is square plus 4 square root over, but this is just frequency square, right, equal to 1, and so implies that k should be equal to n cos of frequency by 4 square, and you computed it to be 3.36. You just substitute that, so 3.36 square square root of 36 square plus 60, so it is around 2.16, okay. So this is this value of the k, right, 2.16, yeah. So this is the value of the k for which you have a phase margin of 40 degree, okay. So is it clear? Okay, so this approach is like similar to the previous one. So you just switch this role of the gain margin and phase margin, then you just compute, okay. So because your phase margin is defined at the gain crossover frequency, so you can, if your phase margin is given, you can easily compute the gain crossover frequency. Once you know this gain crossover frequency, at that point we can compute that data, because at the gain crossover frequency your gain should be 1, right, or it is should be in dB, it should be 0. Similarly, if you are given this gain margin, so your gain margin is defined at the phase crossover frequency, right. So using that data you can find the phase crossover frequency, and depending on what you need at that phase crossover frequency, you compute that other parameter that are required, okay. So you just have to remember these definitions of this phase margin, gain margin and crossover frequency, then this problem is like very trivial, right, so to solve this, okay. So yeah, I had only this question till now. So any doubt, or you have any doubt regarding the courses also, you can ask, okay, or any question if it is not clear, I can repeat that. So any question regarding till now, whatever question you have discussed, any doubt you can ask, okay, or something you want to repeat that is not clear. So I think you have submitted assignment, right, on this. So yeah, okay, yeah, week 6 assignment, okay. So
Yes, sir, submitted.
yeah, okay, so maybe you should have taken this earlier.
Last date is 8.
Okay, yeah, good. So then any doubt you have, you can ask, or we can just end this session, because I don't have any question. I thought because last time it took like more than 2 hours, so I just put 8 question, because last time 10 question it took like 2 hours 11 minutes, so this time actually it took very less time, okay. So
Sir, please, can you explain gain margin and phase margin in a summary way?
okay, yeah. So okay, so just I will explain what are these, okay. So okay, so from this Nyquist plot you already know, or this Nyquist plot is just this polar plot, right. So from that you know that your system will be unstable when it actually crosses that -1 point, right. So at that point -1, what is this gain and angle? So this is this -1 point, right, in the real axis. So what is this magnitude of this point? 1, right, gain, and this angle, it is, if you just compute this, it is 180 degree or -180 degree, okay, whatever you can represent. So we represent it -180 degree. So your system become unstable if it actually passes this point, or actually beyond that point, right. So if it passes through this -1 point, your system is in the verge of instability, that is actually it is reaching the instability beyond this region it will be stable. So these are only valid for non-minimum system, okay, non-minimum phase system. So if there is for non-minimum phase system you don't have any right half plane 0, so you should not encircle your -1 point for stability, right? If there are right hand side pole are there, then this concept is not valid. You have to then use this Nyquist criteria and then check, okay. So as you can see, whatever transfer function it is given, there is no 0 or pole in the right hand side, okay. So you have to be careful of that, okay. So it's just valid for non-minimum phase system, okay, when you have no pole or 0 in the right hand side, okay, for this open loop transfer function, okay. So anyway, so when you cross this instability point, that is the -1, you are in the verge of instability. So if your system is plot is like this for your non-minimum phase system, that means you are not encircling or you are not crossing this -1 point, okay. So from Nyquist criteria, if there is no open loop poles are there in the right hand side, you should not encircle your -1 point, right? So then your system will be stable. So for this green color plot or any plot that is actually this in this side, your system will be what? Stable, right? So now you want to find relative stability, that is how far it is from this instability point. So what is this instability point? This -1, right? In the real axis -1, this is the instability point, and how much far you are from this, that is in the right hand side, how much far you are from your instability point. So this will give you like how relatively stable your system is. So because some kind of disturbance or some kind of in a way you are not actually exactly representing your system, there is some error. So that is possible that if your system plot is like very near to this -1 point, it is possible that you have some error and it actually passes through this, then your system is actually unstable, right? So you want your plot should be something like this, right? Very far from this instability point. So this will give you kind of margin, like how much error you can still make, still you will reach this instability point, right? So is it clear up to now?
Sir, if my system is in instability, then the phase angle is in negative, and the system is stable, then it is coming positive.
Okay, so phase angle will be okay. So for example, your okay, so in your system, okay, so your number of zeros and number of poles, okay, so your number of poles will be always higher than the number of zeros, right? So anyway, at the higher range, your pole contribution will be what? Almost 90 degree, right, for each pole as you move. So it will be always almost, it should be lag system, right? You should not have like a positive angle system, because initially person you can have positive angle as it is passing through like this, the above region, as you can see angle is positive because of the impact of the some zero will be there. So for each zero you have a positive contribution, and each pole you have a negative contribution of minus 90 degree for pole, and for zero 90 degree, right? So initially it can be positive angle, but as you move very high value of frequency, because your number of pole will be either higher or it should be equal to zeros, your system will be in most realistic case it will be lag system, that is it should be negative angle, okay. It is possible that it could have, but more of the system will be negative phase angle, okay. So you want that instability point, you want to avoid that, okay. So this is the -1 point, that is -1 means it has magnitude of 1 and angle of -180 degree, right? And
Okay, means not to sir, we have to only see the negative side.
yeah, I mean, okay, so as I told you, okay, so let me draw this again. So as I told you, your system, okay,
There is means sir, I mean that there is no need to more focus on the positive or negative.
yeah, that's okay, yeah. I mean, mostly you will get negative
Okay,
angle,
sir.
okay, because your, as you can see, there are more poles than the zero in your system, so you will get negative angle always, okay. So it will be initially it can be some positive angle, but as you increase omega, it will go to the negative region because this is the negative angle, right? So if your system is you have an equal number of pole and zero, it will be zero angle, right? It will reach some zero angle, this positive angle zero, it will reach somehow. Okay, like zero order system, you have this type of plot, polar plot. If you remember different type of polar plot, it will reach that. For most practical situation, when you have number of pole are higher, your system will, as omega increases, your system will have a negative angle. And for this non-minimum phase system, you don't have any right half pole, right, in the open loop system. So your Nyquist criteria will tell what? You should not encircle this -1 point, right? So if
Okay,
you
sir.
if you are encircling, then your system is unstable. And if you are passing through -1, then what can you say about that? At what frequency you will pass through this -1? Okay, so one hint will be,
Frequency
okay.
not.
Okay, so you remember from root locus, right? So you use that Routh-Horwitz criteria to find when this you are crossing this imaginary axis, right?
Okay.
Yeah, so that will actually give you that point, right? So when your poles are actually because instability means, okay, so root locus means if your poles are here, then your system is stable, right? And in the root locus, if it is crossing this imaginary axis, at that point, after that you are reaching that instability region. Okay, so this point will be when you are actually crossing that -1 point. Okay, so that you are in the verge of instability, that is your poles are becoming imaginary. So initially they are negative, now they are imaginary at this point, and then it will become positive, so your system will be unstable. Okay, so this is one of interpretation when it actually passes through -1, and you want your pole to be in this region, in the left hand region. So that means your plot should be like this, in the right hand side of this -1 point. Okay, so now the question will be, which of the system will be more stable? Okay, so you have like this kind of system, your plot, this is -1, so one plot is like this for one system is this, so another plot can be like this also, something like that. So now you want to compare which system is like more stable. Okay, so more means you are comparing, means you come to relative part, right? You comparing with one another. So what now, which system is more stable, or in some sense you are concerning about the relative stability. Okay, so that's how this gain and phase margin concept actually comes. Okay, so that means so if you are passing through this -1 point, that means your gain is 1 and your phase angle is what? -180 degree, right?
Sir, relative stability reduces when locus approaches -1 plus J0.
Okay, you can say,
Am I right, sir?
you can also say in Hindi. Okay, if you are not comfortable, I couldn't understand. Can you repeat? You can say in Hindi also, fine.
Sir, I said that the relative stability reduces when the locus approaches -1 plus J0.
Yeah, it's right. Yeah, so you want it to be far from that point, right? And that's how you define this gain and phase margin. So this margin means how much of error you can still afford till you reach this instability point, right? -1. So if your system gain is 1 there, then what should be this angle? For example, okay, first this define its phase angle, phase angle of this point. Okay, what if your system, okay, let's draw this green color. Okay, I'll draw this. Okay, this is one plot. Okay, so at this point, what is this phase angle then for your system? -180 degree, right? And
Yes, sir.
yeah, and if the gain is at that point
We
1,
will
then,
end in instability.
yeah, if it is 1, then your system is unstable, right? So it should, gain should be less than 1, right? This is 0 to -1, so your gain should be in this region, it should be less than 1, right? If it does not encircle this -1 point, its gain should be less than 1, and dB it should be some negative value, less than 0, some negative value. And now you see that if you increase this gain, your plot will be what? It will change this, it will shape will be remain, but it will be shift, right, like this, right? So at one gain it will just cross this -1 point, and you want to find how much gain you can still increase, okay, till you reach this instability point, okay. So that actually gives you gain margin, right? How much gain you can still have this margin of error for this gain, and at what point you are just computing this gain margin? Along this line, right, real line, and that angle is what? -180 degree, right? Is that clear?
Yes, sir.
Yeah. So when this angle is -180 degree, what do you call this? Phase crossover frequency, right?
Yes, sir. In phase margin.
Yeah. No. Phase crossover frequency. I mean, you want your you just compute when this system this polar plot is passing through -180 degree. That means its phase angle is -180 degree, means at the phase crossover frequency you want your gain to be less than 1, right? Is that,
Okay, sir.
yeah.
Clear.
Yeah. So
Yes.
yeah, when your phase angle is 180 degree, you don't want your gain to be 1. You want your gain to be less than 1. So that means when
Less than 1.
yeah, so when your system actually has phase angle of 180 degree, you just call it a phase crossover frequency, because it is passing through -180 degree. So at your phase crossover frequency, you want your gain to be less than 1, right?
Yes, sir.
Yeah. So if you want to compute this gain margin, you just compute when your plot is actually passing through -180 degree. That means when this is crossing this 180 degree or your phase crossover frequency. So at the phase crossover frequency, you see whether your gain is less than 1 or it actually greater than 1. If it is greater than 1, your system is unstable for non-minimum phase system, and if it is less than 1, then you see that your system is stable and you still can reach up to 1. Still this system become unstable. So you compute your phase crossover frequency at that point where your phase angle is -180 degree. You need your system gain should be less than 1 for your non-minimum phase system, when you don't have any right half pole or 0 of your open loop transfer function. So at that point, at the phase crossover frequency, when your system phase angle is -180 degree, you want your gain to be less than 1, and how much gain you can increase is called this gain margin, okay. So you know what is this phase crossover frequency. At that point, you see how much gain still you can increase till you reach this -1 point, that is the gain margin, right? Now you just define this in turn for the phase margin. So then what should be your gain at the phase margin? I mean, at what gain you should compute your phase margin? Because if your system gain is 1, then what should not be the angle at that point?
-180 degree.
Yeah. So when your system plot is crossing 1 magnitude, you call it a gain crossover frequency, right? So at the gain crossover frequency, your system should not be, angle should not be -180 degree. It should be less than that. I mean, how much lag you can still add to that angle. For example, if the angle is 5, then how much angle still you can subtract for that till you reach this -180 degree, okay. So that will give you this phase margin, right? So you compute your gain crossover frequency, that is at point where your gain is 1. You see your system, if your system gain is less than -180 degree, so less than means in the magnitude I'm saying, okay. So if it is like 140 degree -140 degree as we have computed here, so your system is relatively stable. So you see that up to -40 degree you can have here you have this 40 degree of phase margin. That means up to 40 degree you can still lag from this -140 degree till you reach this -180 degree at the gain crossover frequency. So your phase margin is defined in that way. So you first compute when your gain, your actually, I mean, you are crossing your 1 dB, 0 dB or 1 magnitude of gain. So this is called the gain crossover frequency. At the gain crossover frequency, you find the phase angle and see how much error you can still have. I mean, how much angle you can still subtract till you reach this minus 180 degree. So this will give you your phase margin. Okay, so if you are at the gain crossover frequency for a non-minimum phase system, at the gain crossover frequency, if your phase angle is greater than if it is let minus 200 degrees, then what you can say about the system, whether it will be stable or unstable?
So I think it is stable.
No, as I told you, your angle should be okay, your angle because you are increasing your angle, like how I will say, I mean the negative of this angle is increasing, right? So minus 200
Okay,
degree.
okay, sir. Means my system is now instability.
Yeah, instable.
Because it is because it is crossing 180 degree.
Yeah, right. You are right there. So you should be like for this example, as you can see, your angle was at the gain crossover frequency was minus 140 degree, right? You still can have subtract minus 40 can subtract 40 degree till you reach 180 degree, right? So it should be, the magnitude should be less than 180 degree. Okay, the angle magnitude without the negative sign. And because you are lag system, your system is like it is 200 minus 200 degrees, then your system is unstable, right?
Yes, sir.
Yeah, so is it clear?
The question I am seeing in the screen, the system is stable.
Yeah, this is given
because it is minus 140 degree, it is not crossing minus 180 degree.
Yeah. So you are given that you have a phase margin.
Okay, sir, clear.
Yeah, 40 degrees. That means you still can have up to like 40 degrees till you reach that instability, that is the minus 180 degree, right? Yeah. Okay.
Okay, sir, clear.
Yeah. Okay. So if it is clear, then okay, we can end this session and we will meet in the next week. Okay, and still if you have some doubt, you can also ask in the next session also, like regarding any doubt you can ask. Okay, whatever doubt you have, you try. If you still have some doubt, you can ask. Okay, after this, whatever we have covered, you can ask in the next session also. Okay, so we'll stop then.